In the space between stars, there are worlds with no sunrise, no seasons, and no warm parent star to circle. A planet can be thrown free by gravity and spend millions of years crossing near vacuum, lit only by the faintest background glow. This film follows those silent travelers from the widest emptiness of the Milky Way into the hidden physics that keeps them cooling, drifting, and changing in the dark. If this calm science journey helps with sleep, focus, or quiet learning, please like the video and subscribe to the channel for more slow, documentary-style space stories. Far from any sun, space is defined less by objects than by distance. The Milky Way holds hundreds of billions of stars, yet those stars are separated by gaps that are measured in light years. A light year is the distance light travels in 1 year. In the Sun's neighbourhood, the nearest stars are still several light years away, and the space between them is vast enough to swallow many planetary systems. In that spacing, a planet without a host star is not set against a bright sky. It moves inside the same dark volume that lies between all stellar neighbours, where the nearest strong source of heat and light can be far beyond the reach of any warming effect. Starlight does not vanish in interstellar space. It arrives from many directions. The combined output of the galaxy spread thin across a full sky. The Milky Way's band can exist as a faint structure, and individual stars can appear as steady points. Yet the energy of that light is diluted by geometry. With no nearby star, there is no intense beam to warm rock or ice. Illumination becomes a weak glow rather than a driver of climate. Darkness is not absolute, but cold becomes a stable condition because energy input from outside is small. Beyond the glow of stars, there is also a faint background of radiation that fills all of space, the relic light left from the hot early universe. It is real and measurable, and it provides a minimum level of ambient radiation. It does not act like a heater in any ordinary sense. Against it, a drifting world still radiates its own infrared light into space and cools. Without an external lamp, the surface temperature trends downward until it is set mainly by the world's own internal heat, and by how efficiently the surface can lose energy. The planet's larger setting is the Milky Way itself, a disk of stars, gas, and dust wrapped in a more extended halo. In the disk, stars are more common than in the halo, but even there the average spacing remains immense. The probability of a close pass near a star is low for any given stretch of time, and a free-floating planet can travel for millions of years without entering a region where nearby starlight becomes strong. The motion is not aimless in a physical sense. Gravity still shapes the path, yet the shaping comes mostly from the combined mass of the galaxy, rather than from any single nearby star. The result is a long, smooth trajectory through the galactic gravitational field, with slow bending rather than tight circling. Between stars, the material environment is called the interstellar medium. It is made of gas and dust, and it carries magnetic fields and energetic particles. The gas is mostly hydrogen, with helium next, and with heavier elements present in smaller amounts. Its density is extremely low. In many regions there may be only a few atoms in each cubic centimetre, and sometimes fewer. Compared with air at sea level on Earth, this is a near vacuum. For a planet, it means there is almost no drag. The world does not slow in a meaningful way as it travels. It also means there is little material to gather. A drifting planet does not naturally grow by sweeping up gas, because the medium is too thin and the encounter speeds are too high for efficient capture. Dust grains are present as well, minute solids that can be based on silicates, carbon-rich compounds, and ices in colder regions. They matter for astronomy because they absorb and scatter light, but to a planet they are sparse travelers. Impacts occur, yet they are rare and individually tiny. Over long spans, they can alter the outermost surface of exposed ice or rock by slow abrasion and by delivering trace materials, but they do not reshape landscapes quickly. The interstellar medium is more like a thin mist of individual particles than a cloud that can be felt. Energetic particles add another quiet influence. Cosmic rays, often produced by violent events such as supernova explosions, move through the galaxy and strike atmospheres and surfaces. On an airless world, some of these particles can penetrate and break chemical bonds, slowly changing the composition of surface materials. On an icy surface, radiation processing can darken or redden ices and produce new compounds. These transformations are gradual and patchy, limited by how deep the particles reach and by how often new material is exposed. In this wide environment, the word alone becomes a statement about energy and contact. Around a star, sunlight sets a rhythm for temperature, drives winds, and powers surface chemistry. In interstellar space, there is no comparable external engine. If the planet has an atmosphere, it is not heated from above by strong sunlight, and circulation depends more on internal heat and on the physics of gases than on day-to-day warming. If the planet is icy, its surface can become extremely cold, and any volatile gases that reach the surface may freeze out and settle as frost. The surface becomes a place where change is measured in long times, shaped by slow cooling, rare impacts, and persistent radiation. Even in darkness, the planet is not disconnected from the larger galaxy. It carries momentum from its past and continues along a galactic path that reflects where it is and how it moves. It also carries its own stored heat, leftover warmth from formation, along with heat produced by radioactive decay inside rock, can persist for billions of years, leaking outwards slowly. That internal heat does not require a star, and it can keep deeper layers warmer than the surface. Yet the outer boundary remains exposed to a cold, thin medium and a weak sky. The dominant fact of the outer region is still distance, the long separation between stars, and the way that separation turns light into a faint background rather than a nearby presence. In that setting, a drifting world is a solid body moving through near vacuum, surrounded by diluted starlight, and governed by slow galactic gravity. The Milky Way can be understood as a landscape of gravity. Its stars, gas, dust, and dark matter together create a gravitational field that fills a broad volume. A planet that no longer belongs to a single star does not stop being part of this larger structure. It continues to move through the galaxy as a whole, guided by the combined pull of everything around it. In this sense, the planet's most important relationship is no longer with a parent star, but with the galactic mass distribution that shapes long paths over long times. The visible disk of the Milky Way is a flattened system where most stars orbit the galactic center. The Sun is one of those stars, moving around the center along with nearby neighbors. The planet drifting alone tends to share that general motion, because the processes that set it free occur within the disk or near it. Many free-floating planets are expected to be born in star-forming regions inside the disk, then expelled. Their first unbound trajectories are still set within the same moving frame of the galaxy. As a result, many are not traveling as lone bullets leaving the galaxy. They are more often travelers that continue to circle the galactic center, even if their orbits are not tidy or confined to a single plane. In a galaxy, gravity does not come only from the stars that can be seen. Observations show that visible matter is not enough to explain how fast stars and gas orbit in the outer regions. The orbital speeds remain high farther from the center than visible matter alone would allow. This pattern is one of the reasons astronomers infer a surrounding halo of dark matter, a form of matter that does not emit light but adds mass and therefore gravity. The drifting planet moves inside this combined gravitational field. Its path reflects not only the disk of stars but also the extended halo that reaches far beyond the visible edge. For a free-floating planet, the simplest description is that it follows an orbit around the galactic center, like a star does, but with its own particular energy and direction. Over millions of years, that orbit can take the planet through regions where star density changes. It may pass through spiral arms where more gas and young stars are found, then cross interarm regions that are quieter. It may bob above and below the disk plane, because encounters that eject planets can tilt their motion. Each of these movements changes the local environment slightly, but the overall condition of cold, faint illumination persists as long as the planet remains far from any star. The galactic field is smooth on the scale of a planetary system, but not perfectly smooth on larger scales. Individual stars are point masses compared with the planet, and if the planet passes close enough to a star, the star's gravity can significantly bend the planet's path. Such encounters are rare because the distances between stars are large, yet they are not impossible. Over very long spans, small changes accumulate. A planet can have its galactic orbit altered by a few close encounters or by many distant ones that each give a tiny nudge. In dense environments, such as the inner galaxy or within star clusters, these interactions become more common. In the quieter solar neighborhood, they are less frequent. A close pass by a star does not automatically mean capture. For a planet to be captured into orbit around a star, energy must be lost from the planet-star system. Gravity alone, acting between two bodies, typically does not allow a permanent capture because the planet approaches and then leaves on a new trajectory with the same total energy. Permanent capture becomes possible when a third body is involved or when there is some other way to shed energy, such as interaction with a disk of gas or a three-body encounter in which one object takes away energy and another remains bound. In the thin interstellar medium, gas is too sparse to act as a brake. Therefore, most close passes will simply alter the trajectory rather than end the planet's isolation. The galaxy's gravity also shapes the speeds at which objects move. Stars in the disk have typical orbital speeds of hundreds of kilometers per second around the galactic center. A rogue planet shares similar speeds because it is part of the same rotating system. Relative to nearby stars, its speed can be smaller, comparable, or larger depending on its particular orbit. This relative speed matters for encounters. If a planet passes a star quickly, it spends little time in the star's gravitational influence, reducing the chance of capture and limiting the amount of bending. If the relative speed is low and the pass is close, the deflection can be larger. Yet even then, without a way to lose energy, the outcome remains a flyby rather than adoption. The galactic environment is also filled with tidal forces, gentle gradients in gravity that act differently on different parts of an object. For a planet, these tides from the galaxy are extremely weak. They do not stretch the planet in any meaningful way. They also do not heat it. Tidal heating, which can warm moons around giant planets, requires strong gravity differences over short distances, like those near a massive planet. The galaxy is massive, but it is spread out. Its field varies slowly over the scale of a planet. The planet's internal heat is therefore not replenished by galactic tides. Even so, the galactic field has one quiet importance for the planet's long-term story. It determines where the planet can go. A planet that is ejected from a star system does not necessarily leave the galaxy. Many ejections give speeds that are high compared with the star's escape speed, but still low compared with the speed needed to escape the Milky Way's gravitational pull. In those cases, the planet becomes unbound from its star but remains bound to the galaxy. It continues as a galactic orbiting object, part of a vast population of unseen masses. Some ejections, especially those involving very close encounters with massive bodies, may produce speeds high enough to escape the galaxy entirely. Those planets would become intergalactic travelers. Observations and models suggest this should happen, but how often it happens depends on the statistics of the most extreme events. What is clear is that both outcomes exist in principle. Many rogues that remain within the Milky Way, and a smaller fraction that may depart. The planet's relation to the galaxy can also be expressed through what can be measured from afar. The most common way to detect a rogue planet is through its gravity, not its light. When such a planet passes in front of a distant background star, its gravity can act like a lens, briefly magnifying the star's light. The timescale of that magnification depends on the planet's mass and on the relative motion set by their galactic orbits. In this way, the galactic gravity field does not just guide the planet's travel, it sets the background motions that make the planet detectable at all. A rogue planet is therefore both a passenger and a participant in the galaxy's gravitational choreography, moving along a long curve shaped by a hidden mass distribution and occasionally revealing itself by the way it bends another star's light. A drifting planet begins as part of a crowded place. Stars rarely form alone. They emerge from cold clouds that fragment into many dense pockets, each one collapsing into a new star or a small group of stars. In these nurseries, the distances between young stars are far smaller than they will be later, and the space is filled with gas, dust, and the motion of forming systems. The region is not calm. It is structured by gravity, pressure, magnetic fields, and turbulence, and it is shaped by the growing radiation of young stars. Within a star-forming region, a protoplanetary disk can surround a new star. This disk is a flattened mix of gas and dust left over from the collapse that created the star. Dust grains collide and stick, building larger bodies over time. Some of these bodies become the cores of planets. Gas can be captured by larger cores, forming gas giants if the timing and disk conditions allow. In this early stage, the planet is not yet defined by isolation. It is embedded in a system that includes other growing planets, leftover debris, and a disk that still contains a large fraction of the original material. The crowding does not end at the disk's edge. In young clusters, nearby stars pass at distances that would be considered close on the scale of mature stellar neighborhoods. A passing star can tug on a disk, change its shape, and alter the orbits of forming planets. The strength of such a perturbation depends on how close the pass is, how massive the passing star is, and how fast it moves. In many cases, the effect is mild. In some, it can strip away outer disk material or tilt the disk. It can also change the gravitational balance within a young planetary system by adding an external pull at a sensitive moment. A planet's early orbit can be altered even without outside stars, because the forming system itself is full of interacting masses. When multiple planets grow in the same disk, their gravity affects one another. They can exchange energy and angular momentum, the quantity associated with rotation and orbit. These exchanges can push planets into new orbits. They can also lead to close encounters between planets. The system can remain stable if the planets settle into orbits that avoid strong interactions. Stability means that over long spans, the orbits remain bounded and do not cross. but stability is not guaranteed. It depends on masses, distances, and the timing of growth and migration. Migration is a key process in young systems. Planets interact with the gas disk through gravity. This interaction can transfer angular momentum between planet and disk, causing the planet's orbit to shift inward or outward. In many models, a forming giant planet can move inward significantly while the disk still exists. Smaller planets can migrate as well. Migration can bring planets into resonances, orbital patterns where their periods have simple ratios. Resonances can protect systems from collisions by keeping orbits in a coordinated rhythm. They can also create tension because small changes can break the rhythm and lead to instability. As the star's radiation and winds grow stronger, the disk begins to thin and disperse. Gas is removed by heating and by being carried away. When the disk fades, it no longer provides the gentle damping that can calm eccentric orbits. Eccentricity is a measure of how stretched an orbit is compared with a circle. In a gas-rich environment, interactions with the disk can reduce eccentricity and keep orbits relatively orderly. When the gas is gone, the remaining planets interact mainly with each other and with leftover solid bodies. The system becomes more like a gravitational machine made of isolated masses, and small instabilities can grow. A dense stellar environment can increase the chance that a planetary system is disturbed. If a young star remains in a cluster for millions of years, it can experience multiple close passes by other stars. Each pass can slightly reshape the outer parts of the system. Outer planets and distant debris are most vulnerable because their gravity binding to the star is weaker. Even a moderate external tug can change their orbits. Over time, the combined effect can push planets into configurations where they begin to interact strongly. The crowded environment therefore acts as a source of perturbations that can help turn a stable system into an unstable one. Not every star-forming region stays crowded for long. Many clusters disperse, gases expelled by radiation and by supernova explosions from massive stars. When gas leaves, the cluster's gravity weakens and stars drift apart. The early density can fall rapidly. Some stars end up in loose associations, then in the general field of the galaxy. Planetary systems that survive intact continue with them. Others carry scars of the early crowding in the form of tilted or eccentric orbits, truncated debris disks, or planets that have been thrown onto long paths far from their star. In these nurseries, ejection is not an immediate fate for most planets. It is one possible result of rare combinations, strong planet-planet encounters, or planetary systems destabilized by external stellar passes, or systems influenced by the gravity of a companion star. The crowded region is important because it increases the number of close gravitational interactions a young system experiences. It also sets the initial conditions. Planets do not begin their story in a quiet environment and then suddenly become rogues. They begin in a place where gravity is busy, where disks form and dissolve, where multiple bodies grow and shift, and where neighboring stars can pass close enough to matter. Observations support the idea that such environments are common. Many young stars are seen with disks, and many are found in clusters. Exoplanet surveys show that multi-planet systems exist and that some have planets on eccentric and tilted orbits, signs that strong interactions have occurred. These facts align with the view that gravitational rearrangement is part of planetary evolution. Yet the details of how often these rearrangements lead to ejection depend on many factors that remain uncertain, including the distribution of planet masses, the typical architecture of young systems, and the history of stellar encounters in clusters. What is known is that the conditions for ejection are built early, in places where distances are short, motions are frequent, and the developing order of a planetary system is tested before it has time to settle. Inside a young planetary system, order is temporary until it proves itself. Planets form in a disk, but they do not always remain in the calm spacing that long-term stability requires. As masses grow, the gravitational field of the system changes. Small bodies are swept up, scattered, or trapped. Larger bodies begin to dominate their neighborhoods. In this stage, instability is not an unusual failure. It is a natural possibility that emerges when multiple planets share a limited region of space and compete for gravitational control. The simplest stable arrangement is one where planets are separated enough that their gravitational pulls do not drive close approaches. Each planet has a region around its orbit where its gravity is stronger than the star's effect on nearby small objects. When two planets' regions overlap too much, their orbits can be disturbed over many orbits. Small tugs can add up, changing eccentricity and inclination. Inclination is the tilt of an orbit relative to a reference plane. As eccentricity grows, a planet's distance from its star varies more strongly, and its path can cross the paths of other planets. This creates opportunities for close encounters, where the gravity between planets becomes suddenly dominant. Close encounters are a key route to chaos in planetary systems. When two planets pass near each other, they exchange energy and angular momentum. One may lose orbital energy and move inward, while the other gains energy and moves outward. The exchange can also eject smaller bodies into distant orbits. If the encounter is close enough, it can throw one planet onto an orbit that either collides with the star, collides with another planet, or becomes so elongated that it reaches far into the outer system. A sequence of such encounters can transform a system's architecture over a relatively short interval, measured in thousands or millions of years, which is brief compared with the age of a star. In many models, giant planets are the strongest drivers of instability because their masses are large. Their mutual encounters can deliver large velocity changes. A system with two or more giant planets can be especially sensitive to spacing. If their initial orbits are too close, long-term stability becomes unlikely. The system can still survive if the planets fall into a resonant configuration, where their orbital periods lock into a repeating pattern. Resonances can prevent close approaches by controlling the relative positions of the planets along their orbits. But resonances are not always permanent. Migration during the disk phase can move planets into resonances, then later changes can break those resonances. Disk dispersal is a turning point. While gas is present, it can act like a cushion. Gas exerts forces that can damp eccentricities and inclinations. It can also provide a medium that encourages planets to migrate smoothly, rather than jump through violent encounters. When the gas is removed, that cushioning disappears. The planets remain, now moving under their own gravity, and the star's gravity with fewer stabilizing influences. If the orbits are already close or resonant, the loss of damping can allow instabilities to grow. Some systems become more stable after gas dispersal, because migration stops and spacing freezes. Others become less stable, because the remaining configuration is precarious. Small bodies contribute as well. Leftover planetesimals, the building blocks of planets, can form belts and scattered populations. When a giant planet interacts with these bodies, it can exchange angular momentum with them. By scattering many small bodies inward or outward, a giant planet can slowly shift its own orbit. This process can move planets into new resonances or out of old ones. It can also stir the orbits of other planets indirectly. Over time, a quiet background of small body scattering can nudge a system toward instability, especially if the planets are already near the edge of stability. Companion stars add a further layer of complexity. Many stars are in binary or multiple systems. A companion star can orbit at a distance ranging from close to extremely wide. Even a wide companion can affect the outer parts of a planetary system by adding a periodic gravitational pull. This pull can tilt or stretch orbits. In some circumstances, it can cause cycles where a planet's inclination and eccentricity trade off, raising eccentricity high enough that the planet's path crosses other orbits. The details depend on geometry and distance. It is not a universal outcome, but it is another mechanism by which early stability can be compromised. In this setting, instability is not a single event but a process. It begins with small deviations that grow under repeated gravitational interactions. A planet may first develop a slightly more eccentric orbit. It then begins to approach another planet more closely at certain points. Those approaches become closer over time. Eventually, a strong encounter occurs, and the system enters a scattering phase. In scattering, planets repeatedly pass near each other over many orbits, changing trajectories each time. This phase can end in several ways. Planets may collide, merging or destroying each other. A planet may be thrown inward and later lost to the star. Or a planet may be thrown outward onto a path that reaches beyond the system's outer boundaries. The energy needed to unbind a planet from its star is not always extreme, especially for planets that are already far out. A planet on a wide orbit is less tightly bound. A modest additional speed, delivered at the right point in its orbit, can make its path unbound. An unbound path is one where the planet's speed relative to the star is above the star's escape speed at that distance. In such a case, the planet no longer follows a closed ellipse. It follows an open trajectory and leaves the system. The direction it leaves depends on the geometry of the last encounter. The speed it carries away depends on the details of the interaction and the mass of the planet that provides the final kick. The end result can be a planetary system that looks calmer than it once was. After scattering ends, the surviving planets may be fewer and more widely spaced. They may have more eccentric or tilted orbits than before. The system may contain a scattered population of debris. To an outside observer, such a system can appear as a stable arrangement that has simply existed for a long time. Yet the present architecture can be the residue of a brief period of violent rearrangement in its youth. Not all ejections require giant planets, and not all instabilities are dramatic. In systems with many smaller planets, gravitational interactions can still lead to collisions and to the removal of some bodies. However, the most efficient way to throw a planet completely free is through interaction with a much more massive planet, or through a sequence of encounters that builds up speed. Therefore, many models predict that ejections are often linked to the presence of giant planets, or to environments where external perturbations make encounters more frequent. What remains uncertain is the exact frequency. Observations show that some planetary systems are compact and stable, while others contain planets on eccentric orbits that suggest past scattering. The existence of rogue planets inferred from microlensing supports the idea that ejection happens. Yet the distribution of masses and the total number of rogues depend on how common these unstable phases are. In the inner region of the topic, the focus stays on the system itself, where early formation creates a busy arrangement. Disk dispersal removes damping, and gravity takes over as the main sculptor. Here, the path toward becoming a drifting world is built step by step, through instability that grows from simple orbital mechanics. Ejection is a transition from being bound to being free. In orbital mechanics, bound motion around a star means the planet's total energy relative to that star is negative. The planet's speed is not enough to escape the star's gravity. unbound motion means the total energy becomes zero or positive. The planet's trajectory opens outward and it does not return. This change can occur suddenly during a close encounter, when a planet receives a sharp change in speed and direction. It can also occur through a sequence of smaller changes that gradually raise the planet's energy until one final encounter crosses the boundary. In most cases, the immediate cause is gravity alone, acting during a near pass between planets. When two planets approach each other, their mutual gravity accelerates both bodies. The exchange does not create energy from nothing. It transfers energy between the planet's orbits around the star. One planet is left more tightly bound, with a smaller orbit, while the other is pushed outward, with a larger orbit and greater orbital energy. This is the core of scattering. The larger the masses involved, the larger the possible transfer. A massive planet can act as a gravitational engine that gives a smaller planet a strong push. The most effective ejections tend to involve giant planets. A Jupiter-like planet has a deep gravitational well and a strong ability to redirect the motion of smaller bodies. In a young system with multiple giant planets, encounters can be strong enough that one of the giants itself is expelled, but more commonly a lower mass planet is removed. This depends on the system's mass distribution and on how close the encounters become. A planet that passes within a few planetary radii of a giant can receive a large velocity change. The encounter is brief, but it can decide the planet's future. The geometry of an encounter matters. The change in speed delivered depends on the relative velocities, the approach distance, and the angle of the flyby. There is also a preferred time for ejection near the outer part of the planet's orbit, where its speed around the star is lower and the escape speed is also lower. A given additional velocity is more likely to produce escape there. Scattering tends to increase eccentricity, often placing planets on elongated orbits that swing close to the star and then far away. As those orbits stretch, the planet spends a long time near its farthest point. This provides repeated chances for encounters with outer planets and makes it easier for one strong kick to push it over the escape threshold. Perturbations from other stars can assist. In a stellar cluster, a passing star can weaken the star's hold on distant planets by adding an external tug. It can raise eccentricities or tilt orbits. It can also strip outer bodies directly if the pass is close enough. The effect is strongest on planets that already lie far from their star. A wide-orbit planet is less tightly bound and therefore easier to disturb. In this way, external encounters can prime a system by making wide orbits more eccentric and bringing planets into crossing paths. The final ejection may still be caused by planet-planet interaction, but the initial destabilization can come from the surrounding environment. Binary stars can do something similar from within the system itself. If a planet orbits one star of a binary, the companion star provides a periodic gravitational perturbation over long spans. This can change the planet's orbital shape and tilt. In some configurations, the perturbation can drive cycles that raise eccentricity. High eccentricity can lead to close approaches with other planets, or to passages so close to the host star that tides or collisions remove the planet. The pathway to a rogue planet in a binary system often involves the same basic ingredient as in a single star system, a way to turn stable spacing into crossing orbits and close encounters. Once a planet becomes unbound, it leaves the system on an open trajectory. Initially, it departs through the outer regions where the star's pull is weakest. It continues to be influenced by the star for some time. Even after the orbit becomes unbound, the planet must travel outward, gradually losing the star's grip as distance grows. The planet carries away a hyperbolic excess speed. the speed it would have far from the star if no other forces act. This speed can be modest compared with the orbital speed near the star, because only a small amount above escape is needed to leave. In many cases, the planet's speed relative to its former star may be a few kilometers per second. The exact value varies widely. The direction of travel is set by the last encounter and by the planet's position in its orbit at the time. This means a rogue planet's motion is not necessarily aligned with the ecliptic plane of its former system. It can leave at an angle, carrying a tilted path into the galaxy. The planet may also leave with a rotation state and a moon system that reflects its former life. Some ejections may strip moons away, some may keep them. A moon that remains bound must stay within the planet's own gravitational sphere of influence during and after the ejection. Strong encounters can disturb that region. Whether moons survive depends on how violent the last scattering event is and on how tightly the moons orbit the planet. After ejection, the planet enters interstellar space as a cold traveller. At first, it still contains heat from formation and from the long internal cooling that occurred while it orbited its star. If it was once warmed by starlight, that warming stops. The surface begins to cool toward a new equilibrium set by internal heat and weak background radiation. Any surface volatiles that depended on sunlight to stay gaseous may condense. An atmosphere may collapse onto the surface as frost if temperatures drop below the freezing point of its main gases at the ambient pressure. This does not require dramatic change. It is a slow adjustment over time, controlled by heat flow and by how quickly the atmosphere can radiate energy into space. The planet's trajectory then becomes part of the galactic population. It travels along a path shaped by the Milky Way's gravity. It passes through regions with different densities of gas and dust, and through varying fields of cosmic rays. It does not usually encounter anything large. Interstellar space is wide. The planet's chief interactions are with the thin medium and with radiation. What can be said with confidence is that ejection is a plausible and natural outcome of gravitational dynamics in young planetary systems, especially those containing multiple massive planets, or those subject to perturbations from other stars. What remains uncertain is how often each pathway dominates and how many planets are removed from systems over the galaxy's history. Observational methods that detect rogues by microlensing indicate that such objects exist, and theoretical models show that scattering can produce them. In this region of the topic, the focus stays on the transition itself, the physical boundary between bound and unbound motion, and the quiet fact that a planet can become alone not by losing substance, but by gaining a small amount of speed at the right moment. Not every lonely world is necessarily born as a planet in the familiar sense. In astronomy, there is a range of masses between planets and stars, and nature can produce objects across that range through more than one process. A star forms when a region of gas collapses under gravity and becomes hot and dense enough at its center to sustain hydrogen fusion. A planet, in the usual picture, forms from the disk of material around a young star. Yet the boundary between these pathways can blur at low masses, because collapsing gas can fragment into clumps, and some clumps can be too small to ignite sustained fusion. These objects can be planetary in mass while not having formed in a disk around a star. One class of such objects is commonly called a brown dwarf when it's more massive than planets but less massive than stars. Brown dwarfs can form like stars by direct collapse of gas. They can fuse deuterium for a time if their mass is high enough, but they do not sustain hydrogen fusion like a true star. At the low end of mass, there are objects that may overlap with giant planets in mass, and the distinction becomes a matter of origin rather than simply mass. Observations show that young star-forming regions contain free-floating objects with masses estimated to be in the planetary range. Some appear alone, not clearly bound to any star. For these, the question becomes whether they are ejected planets or low-mass products of cloud collapse. There are clues, but they are not always decisive. An object formed in a disk around a star can inherit a composition and a structure shaped by that disk environment. An object formed by direct collapse may more closely resemble a small star in its early structure, with a larger fraction of its mass in a hot interior at formation. However, both kinds of objects cool with time, and their emitted light becomes faint. At great distances, in cold conditions, the differences can be hard to measure. Spectra, the distribution of light by wavelength, can provide some information about atmospheric composition and temperature, but translating that into a clear formation history is challenging. The mass of an object can help suggest a pathway, but it is not a perfect guide. Disk formation is efficient at producing low to moderate mass planets. It can also produce gas giants. Cloud collapse more naturally produces stars and brown dwarfs, and the formation of very low mass fragments may require special conditions. Some models allow fragmentation down to a few Jupiter masses, especially in dense, turbulent regions, but the frequency of such events remains uncertain. Therefore, when a free-floating object is found to have a mass similar to Earth, the disk and ejection pathway becomes the more likely explanation. When an object is much more massive, the formation pathway becomes less clear, and both origins may be plausible. The recent ability to estimate the mass of some free-floating planets more directly strengthens this distinction. When a microlensing event is observed from two well-separated locations, such as Earth and a spacecraft, the geometry can allow the distance to the lensing object to be constrained. With the distance and the event timescale, the mass can be inferred more reliably. A case where the inferred mass is close to that of Saturn supports the idea that a true planet, formed in a disk, can be found wandering in the galaxy. It does not prove that every free-floating object is an ejected planet, but it demonstrates that ejection can produce a planet mass traveler that persists long after its escape. Even within the ejection pathway, there are different flavors of origin. Some rogues may be planets that formed close to their star and migrated outward before instability, then were expelled. Some may have formed farther out and been thrown away with less difficulty. Some may have been stripped from their star systems during close stellar encounters in clusters. These variations matter because they affect the planet's initial heat content, composition, and possible moon system. Yet from the outside, a rogue planet's defining trait remains the same: it does not orbit a star. The boundary between ejected planets and star-formed low-mass objects also matters for population studies. Microlensing surveys count objects based on how often they produce lensing events of certain timescales. Timescale depends on mass, but also on the relative speed and distance. If an observed population includes both ejected planets and low-mass collapse objects, then interpreting the counts requires care. A bump in the distribution of event durations could be read as a large population of Earth mass rogues, or it could reflect a mix of masses and distances. Improved measurement methods help reduce this ambiguity, but they do not eliminate it. Another possible pathway to free-floating status is the disruption of star systems themselves. In the galaxy, stars can be lost from clusters, and binary systems can be torn apart by gravitational encounters. If a star that hosts planets is ejected from a cluster, or perturbed strongly, its planets can be destabilized. In extreme cases, a star could be stripped of some planets without the planets being directly scattered by other planets. This is still a gravitational encounter story, but it emphasizes the wider environment and the vulnerability of outer orbits. The science remains careful about what is known and what is uncertain. Observations indicate that free-floating planetary mass objects exist. Observations and models indicate that planet-planet scattering and cluster encounters can eject planets. Observations also indicate that low-mass objects can form without being bound to a star. At least in some regions, it remains uncertain, for many individual objects, which pathway applies. It also remains uncertain how the balance of pathways changes with environment, such as dense clusters versus more isolated star formation. Within the inner progression of the topic, the focus now stays on origin classification, because understanding what a drifting world is requires knowing what kinds of bodies the category includes. A rogue planet can be an ejected member of a planetary system, carrying the chemical history of a disk. It can also be a planetary mass object formed by direct collapse, sharing some traits with brown dwarfs. The distinction is not always visible from a distance, especially after long cooling. What can be done is to use mass estimates, kinematics, and population patterns to narrow the possibilities, always separating what measurements show from what origin stories they suggest. A free-floating planet is difficult to find because it has no nearby lamp. A planet seen in reflected light depends on starlight. A planet seen in thermal emission depends on its own heat. When a planet is young, it can still be warm from formation, and it can radiate infrared light strongly enough to be detected at some distances with sensitive instruments. As it ages, it cools. The rate of cooling depends on mass, composition, and atmosphere, but the trend is steady. Over hundreds of millions to billions of years, a planet without external heating becomes cold at the surface. Its glow fades into the background. In visible wavelengths, the planet is almost invisible. It reflects only the faint background starlight of the galaxy. Even a large planet reflects little, because the illumination is so weak. In infrared, the planet emits according to its temperature. At tens of degrees above absolute zero, the peak emission is at longer wavelengths that are difficult to measure against cosmic backgrounds and instrument noise. A planet might still be detectable if it is nearby and if it is large enough to emit measurable heat. But the population that matters for understanding rogues is not limited to young and nearby objects. It includes old travelers spread across the galaxy. For those, direct detection by emitted light becomes rare. An atmosphere can both help and hinder detectability. A thick atmosphere can trap internal heat and keep the surface warmer than it would be without one. This can increase infrared emission, yet atmospheres also absorb and re-radiate energy, shaping the spectrum in complex ways. At low temperatures, many gases condense: nitrogen, carbon dioxide, methane, and water vapor. Each have different condensation behavior. At the cold temperatures expected for a starless world, common gases may freeze out onto the surface, leaving a very thin atmosphere or none at all. In such a case, the surface radiates heat directly into space, and cooling can proceed efficiently. Even if the planet cannot be seen by its light, it still has mass. Mass affects gravity, and gravity affects light passing nearby. This leads to one of the most powerful ways to detect rogue planets: gravitational microlensing. In microlensing, a foreground object passes near the line of sight to a distant background star. The foreground object's gravity bends the light rays. The result is that the background star appears brighter for a short time. The foreground object can be a star, a brown dwarf, a planet, or even a smaller mass. The key is that the lens does not need to emit light. It can be dark. Its gravity is enough. Microlensing events are rare and brief. They require alignment, and the alignment must occur as objects move. Surveys look toward dense star fields, such as the galactic bulge, where many background stars provide many opportunities. When an event happens, it is recorded as a smooth change in brightness of a background star. The shape of that change, the light curve, depends on the lens mass and the relative motion between lens and source. A low-mass lens produces a short event. A higher mass lens produces a longer event. For a planet mass object, the event can last from hours to days, depending on mass and geometry. This method reveals the presence of a lensing mass, but it does not automatically reveal all its properties. The event timescale depends not only on mass, but also on distance and speed. A nearby low-mass object can produce a similar timescale to a farther higher-mass object. Without additional information, the mass and distance can remain uncertain. This is a central limitation of microlensing when observed from a single location. It means that a single light curve often cannot uniquely identify whether the lens is an Earth mass rogue, a more massive object farther away, or a different mass at a different speed. This difficulty has shaped the history of rogue planet claims. Surveys have reported short-duration events consistent with planetary mass lenses. Interpreting these events requires assumptions about typical distances and velocities based on models of the galaxy. Those models are grounded in measurements of stellar populations and motions, but they still produce a spread of possibilities for any individual event. As a result, population estimates have carried uncertainty. When surveys infer how many rogue planets exist, they must account for the detection efficiency of their instruments, the distribution of source stars, and the likely distribution of lens distances and speeds. Small changes in assumptions can lead to different inferred abundances, especially for low-mass planets. Other detection methods exist but are narrower in scope. A rogue planet could be detected if it passes in front of a star and causes a transit, but this is extremely unlikely because the planet is not bound to the star and alignments are rare. A rogue planet could be detected through its gravitational influence on a nearby star's motion, but this requires the planet to pass close enough and to be massive enough, and it requires precise astrometric measurement over time. Astrometry is the measurement of a star's position in the sky. It is powerful, but for free-floating planets it tends to be useful mainly in close encounters that are themselves rare. In the outer part of the detection problem, the core fact is that rogues are dark, cold, and dispersed. The galaxy is large, and even if rogue planets are numerous, the average distance between them may still be vast. Detection therefore relies on chance alignments and on patient monitoring of millions of background stars. When a microlensing event is found, it provides a brief window where the planet's presence is felt as a change in light from something else. This observational reality shapes what can be known. A rogue planet is not typically discovered as a resolved disk or a visible globe. It is discovered as a pattern in a light curve. From that pattern, astronomers infer the existence of a lensing mass and estimate its mass range. The planet remains unseen as an image, and yet it becomes part of the catalogue of worlds. The science of rogues therefore rests on careful statistics, on the physics of gravity's effect on light, and on an acceptance that most individual objects will remain dim travellers, glimpsed only by the shadows and brightenings they impose on distant stars. Gravitational microlensing is a method built from a simple fact of relativity mass bends spacetime, and light follows the curved paths. When a foreground object passes close to the line of sight to a background star, the light from the background star is deflected. The deflection is small in angle, but it changes how much light reaches an observer. In perfect alignment, the background star's light can be arranged into a ring-like pattern around the lens. In most cases, the alignment is not perfect, and the result is a temporary brightening rather than a visible ring. The effect is called microlensing because the apparent angular separations are too small to resolve for most events, and the lensing is detected as a change in brightness over time. The lens can be any compact mass. A star often produces a long-duration microlensing event. A planet mass lens produces a shorter one. The timescale is commonly described by how long it takes the alignment to pass through the region where lensing is significant. That region is set by the Einstein radius, a scale that depends on lens mass and on the distances between observer's lens and source. The details are technical, but the core point is that heavier lenses have larger Einstein radii, and therefore their lensing signatures tend to last longer when relative speeds are similar. For a rogue planet, the Einstein radius is small, and the event can be brief. Microlensing surveys are designed to watch many stars at once because events are rare. A single star is unlikely to be lensed at any given moment, but in dense star fields, millions of stars can be monitored continuously. Small fractions of them brighten at any time due to lensing. These brightenings are distinguished from other variability by their characteristic smooth shape and by the way they occur without the color changes typical of many stellar flares. In practice, careful analysis is needed because stars have many kinds of intrinsic variability. An instrumental effect can mimic small changes. The reliability of microlensing detections improves with high cadence observations, stable photometry, and repeated measurements. When a microlensing event is caused by a rogue planet, there is usually no detectable light from the lens itself. The brightening of the background star is the only signal. The light curve can often be described by a simple model with a small set of parameters: the time of peak magnification, the maximum magnification, and the event timescale. For planetary lenses, additional subtleties can appear if the lens has a moon, or if the source star has a finite size that matters when the alignment is very close. In many cases, though, the signal remains simple and short. The same simplicity is what makes the mass hard to pin down from a single viewpoint. The event timescale mixes mass with geometry and motion. A short event suggests a low-mass lens, but it could also arise from a faster relative motion or a closer lens with different geometry. Astronomers use models of the galaxy's structure and velocity distribution to estimate probabilities. They can say that certain masses are more likely given the observed timescale and the typical distribution of lens distances. This is a statistical inference. It becomes stronger when many events are collected. For individual events, uncertainty can remain large. In spite of these limitations, microlensing is uniquely sensitive to planets that are far from their stars, and to planets with no stars at all. Other methods tend to favor planets close to stars, because transits and radial velocity signals are stronger there. Microlensing does not require the planet to be close to a star. It detects mass wherever it lies along the line of sight. This makes it one of the few practical tools for building a census of rogue planets and of distant, cold planets that would otherwise be hidden. The timescale differences are meaningful. An Earth mass lens typically produces an event lasting on the order of hours to a day, depending on geometry. A Jupiter mass lens can produce events lasting days. A star can produce events lasting weeks or months. These are broad tendencies rather than exact rules, but they guide how surveys plan their cadence. To detect Earth mass rogues, a survey needs frequent measurements, because a peak can be missed if observations are too sparse. This is one reason why space-based observatories, with stable viewing and minimal interruptions, are attractive for microlensing studies. Microlensing also has an inward direction in the science. The signal is a change in brightness, but the ultimate target is the hidden mass that causes it. Astronomers attempt to extract more information by using subtle features of the light curve. If the source star's finite size matters, the light curve's peak can be rounded in a way that provides extra constraints. If the lens is close enough, its motion can create slight asymmetries. If the observer is not stationary, the changing viewpoint as Earth orbits the Sun can also introduce distortions. These effects can provide hints about lens distance and relative motion, but in many short planetary events they are small. The observational context is also shaped by the fact that lensing does not repeat. A rogue planet does not orbit a star that can be monitored for periodic signals. The alignment occurs once, and then the planet continues on its path. This makes each event a single chance to learn. Follow-up observations must be rapid, and coordination between observatories becomes valuable. Ground-based networks can watch around the clock by using telescopes at different longitudes. Space-based telescopes can provide a stable second viewpoint or can fill gaps that Earth-based observing cannot cover. In this region of the topic, microlensing becomes the primary way in which lonely worlds are revealed. The science is a translation from a temporary brightening into a statement about mass. It is careful, because the translation is not unique without extra information. Still, the method is grounded in well-tested physics and has a strong record of finding exoplanets in general. For rogue planets, it offers something rare, a way to detect a world even when it shines almost not at all, by letting gravity do the work of announcing its presence. A microlensing light curve can be precise and still leave key properties unknown. The curve records how the brightness of a background star changes with time. From that change, a characteristic duration can be measured, yet duration is not mass alone. It is the combined result of lens mass, distances, and relative speed. Distance matters twice. The lens must be somewhere between the observer and the source star, and the geometry determines the scale of the lensing region. Speed matters because the event is a moving alignment. A fast passage through the lensing region yields a short event even for a larger mass, while a slow passage yields a long event for a smaller mass. For a typical microlensing event observed from a single location, the measurable quantities are limited. The background star brightens, reaches a peak, and returns to normal. The event's symmetry and shape can be described by the simplest lens model. The timescale is a fitted parameter, yet the timescale is proportional to an angular scale divided by an angular speed. The angular scale depends on mass and geometry. The angular speed depends on the relative proper motion between lens and source as projected on the sky. Proper motion is the apparent motion of an object across the sky, usually measured in tiny angular units per year, arising from its real velocity and distance. In microlensing, the lens and source have their own proper motions because they orbit within the Milky Way. The observer has motion as well, because Earth moves around the Sun and the Sun orbits the galactic center. When only one light curve is available, there is often a degeneracy, meaning different combinations of mass, distance, and speed can produce similar curves. A nearby lens of modest mass might mimic a distant lens of smaller mass. A lens in the disk might mimic a lens in the bulge depending on the relative motions. This is not a flaw in the physics, it is a consequence of limited information. The light curve is a one-dimensional record of brightness over time. It is powerful, but it does not automatically encode all dimensions of the system. For long events, some additional effect can help. Earth's orbit can create a slight distortion in the light curve, called microlensing parallax, because the observer's position changes during the event. That distortion can provide information about the lensing geometry for short events caused by planetary mass lenses. The event may end before Earth's motion produces a detectable effect. In those cases, the parallax signal is often too small to measure from Earth alone. Another potentially helpful effect, the finite size of the source star, can also be hard to detect unless the alignment is extremely close. Many events do not pass close enough for the source's angular diameter to leave an imprint. Without these extra signals, the mass and distance remain coupled. The consequence is that many candidate rogue planet events can be described as consistent with a range of masses. A short event can suggest a planet mass lens, but the exact planet mass can be uncertain. This uncertainty propagates into population estimates. Surveys count events of various durations and then infer how many lenses of various masses must exist to produce them, given assumptions about the Milky Way structure and velocities. If the distances and speeds of lenses are not well constrained, then the mapping from timescale distribution to mass distribution is broad. This is why independent constraints are valuable. If the distance to the source star is known, that reduces one set of uncertainties. Many source stars toward the galactic bulge can be assumed to lie at similar distances, but there is still a spread. If the lens emits light and can be detected after the event, then its brightness and color can help estimate its mass and distance. But for rogue planets, the lens is typically too faint. If the lens is a star with a planet, additional features called caustics can appear in the light curve, revealing the planet-to-star mass ratio and separation for a true rogue planet. The absence of a host star signal is part of the story, but it also removes an anchor that could otherwise help. In some cases, a long-term follow-up can help. After the event, the lens and source continue to move relative to each other. If their separation becomes large enough, high-resolution imaging can sometimes detect the lens directly if it is luminous. This method has been used for stellar lenses and for some exoplanet hosts. For rogue planets, it is typically not available because the lens remains dark. The separation of lens and source still occurs, but there is no lens light to see. Therefore, the event remains a transient signature without a luminous counterpart. A further complication is that not every short event must be caused by a free-floating planet. A planet bound to a star at a very wide separation can act, for microlensing purposes, almost like a separate lens. If the host star is far enough away in projection, the planet's lensing signal can occur without an obvious simultaneous lensing signal from the star. Such a planet is not free-floating, but it can appear as one in microlensing data if the host star's contribution is not detected. Distinguishing truly unbound planets from widely separated bound planets requires careful analysis and often additional information. Survey teams treat this as a known ambiguity, and they attempt to account for it in population models. Yet for many individual events, uncertainty remains. This is the measurement problem at the heart of rogue planet science. Observations indicate that short microlensing events occur. Their timescales suggest planetary masses. It remains uncertain, in many cases, whether the lens is unbound or is a wide-orbit planet with an undetected host star, and it can remain uncertain what the exact mass is. The uncertainty is not a failure. It is a boundary set by the available data. The path inward from this region is toward methods that can break the degeneracy. The recognition is that a single line of sight from a single location does not provide enough geometry. To improve, observers need a second viewpoint separated by a large distance. That separation creates a measurable difference in how the event looks, because the alignment is slightly different from the two locations. With that difference, the lens's distance and mass can be constrained more tightly. This is why coordinated observations involving Earth and space, or multiple space platforms, matter so much for the study of lonely worlds. The limitations of single-view microlensing define the problem clearly, and they also define the direction of progress. A second viewpoint turns microlensing from a single shadow into a piece of geometry. When an event is observed from Earth alone, the light curve is shaped by one line of sight. If the same event is observed from a location far from Earth, the alignment differs slightly. The peak time, the peak magnification, and the detailed curve can shift. These differences arise because the observer's position changes the apparent separation between lens and source on the sky. This is the basis of microlensing parallax measured by simultaneous observations, and it can reduce the uncertainty that comes from a single curve. The concept is simple even when the implementation is demanding. A lensing event is defined by the lens passing near the line of sight to the source star. From Earth, that nearest approach happens at a certain moment and at a certain minimum separation. From a spacecraft far away, the lens may pass slightly closer or slightly farther, and the moment of nearest approach may occur earlier or later. If the separation between Earth and the spacecraft is large enough, the differences become measurable. The larger the separation, the stronger the parallax signal. A separation comparable to the distance between Earth and the Sun is especially useful, because it creates a baseline large enough to matter for many events. With a parallax measurement, the event's geometry can be constrained. In microlensing, one of the key quantities is the projected Einstein radius, a scale that combines mass and distance information. Parallax helps estimate this scale. If the finite size of the source star can also be measured, then another quantity, the angular Einstein radius, can be inferred. Together, these can yield the lens mass and its distance more directly. For many planetary mass events, the finite source effect may not be detectable, but parallax alone still provides strong additional constraints by narrowing the range of possible distances and therefore the range of possible masses. In practice, the need is coordination. Ground-based surveys can detect events and issue alerts quickly. Space-based observatories can then monitor the same source star at high cadence. This is easiest when the Space Telescope is already looking toward the relevant star fields. Some missions have done this in focused campaigns. The advantage of space observations is stable imaging without atmospheric noise and with a continuous view not interrupted by day-night cycles or weather. The advantage of ground observations is flexibility and wide coverage. Together, they create the chance to catch a short planetary event from two locations. The baseline between Earth and a spacecraft is not fixed. A spacecraft in an Earth-trailing or Earth-leading orbit around the Sun gradually separates from Earth over time. The difference in viewpoint grows, then changes. This changing separation can be an asset, because it can tune the parallax sensitivity. For some events, the baseline yields a strong difference in curves. For others, the geometry is less favorable. Therefore, many events are needed to build a robust sample with well-measured parallax. When the parallax is well measured, the result can be a more confident statement about the lens. Instead of a broad range of masses, the mass estimate narrows. Instead of uncertainty about whether the lens lies in the disk or bulge, its likely distance becomes clearer. This is crucial for rogue planets, because it helps distinguish between a truly low-mass planet nearby and a different mass farther away. It also helps separate an unbound planet from a wide-orbit planet around a star if the host star would be detectable at the inferred distance. If the lens is close enough and massive enough, and if it were a star, it would likely be visible. If no such light is seen, the lens is more likely to be planetary. A recent example demonstrates the value of this approach. A microlensing event observed from Earth and from a space-based platform can be modelled with enough geometric constraint to infer a planet mass comparable to Saturn, and to estimate that the lens lies within the Milky Way. The event is still transient and the planet remains unseen as an image, but its mass is no longer a vague possibility. It becomes a measured quantity within stated uncertainties. This kind of result strengthens the case that at least some rogue planets are ordinary planets in mass, made in planetary systems and later expelled. Even with parallax, there can remain degeneracies. The projected geometry can sometimes be mirrored in different ways, producing similar light curves. These are known as parallax degeneracies. Where multiple geometric solutions fit the data, additional observations can help break them, such as more precise photometry, measurements in multiple wavelengths, or simultaneous observations from more than two locations. Yet even when some degeneracy remains, the space and ground combination typically reduces uncertainty significantly compared with a single viewpoint. This method also changes population studies. If a survey can measure parallax for a subset of events, it can calibrate how event timescales map to mass and distance more reliably. It can then improve the interpretation of events without parallax by using the calibrated distributions. Over time, this reduces the uncertainty in the inferred number of rogue planets of various masses. It also improves the ability to test formation models. If the population includes many Earth mass rogues, that supports frequent ejection of small planets or a common formation pathway for low-mass free-floating objects. If the population is dominated by larger masses, that suggests different dynamics. The inward direction is still observational, but it moves toward instruments designed to do this work at scale. A mission that can monitor dense star fields continuously, with high cadence and stable photometry, can detect many short events. A mission that has a wide field of view can watch many stars at once. A mission placed in space naturally provides a different viewpoint from Earth, and if ground observations are also available, the parallax baseline can be exploited. This is the context in which future surveys become important. The challenge is not only to detect rogue planet candidates, but to weigh them well enough to place them on a mass scale with confidence. Parallax is one of the main tools that allows this weighing. In this region, the lonely planet is still found through a background star's brief brightening. Yet the additional viewpoint gives depth. It turns a time series into a spatial constraint. It narrows what can be claimed. It also shows how a planet that emits almost no light can still be studied with physical rigor, not by seeing it, but by triangulating its gravitational effect from multiple places within the solar system. When a microlensing event is recorded from more than one vantage point, the lens stops being only a suspicion of mass and becomes something closer to a measured object. The event still appears as a temporary brightening of a background star, but the differences between the curves carry information about where the lens is and how heavy it must be. In the case of a free-floating planet candidate whose mass is estimated to be comparable to Saturn, the importance is not in the drama of discovery, but in the demonstration of method. A planet mass body can be detected and weighed even when it is not bound to a star and emits almost no detectable light. A Saturn mass scale is significant because it sits comfortably within the range of planets that form in disks around stars. Saturn is a gas giant with a mass far below the threshold for sustained fusion. A free-floating object with a similar mass is not easily explained as a conventional brown dwarf, especially if its mass estimate is robust and does not extend into the higher range. This does not prove it formed in a disk. but it makes the disk and ejection pathway plausible. It also shows that the galaxy contains planetary mass lenses that are not merely hypothetical. Their gravity is enough to register in microlensing surveys, and their masses can be constrained when geometry is known. The way such a mass estimate is reached is careful. The light curves from Earth and space provide the parallax signal, which constrains the projected scale of the lensing geometry. The event duration provides a timescale. Together, these limit how large the Einstein radius can be, and therefore how massive the lens must be. If the source star's size effect is also measured, it can provide an angular scale and further tighten the solution. Even when the source size effect is not clearly detected, the parallax information still shrinks the allowed mass range compared with a single view fit. The result is not an exact number without uncertainty, but a constrained range that can be placed alongside familiar planetary masses. The location of the lens matters as well. A lens closer to Earth would produce a different parallax signature than a lens near the galactic bulge. By fitting the two curves, astronomers can estimate where along the line of sight the lens is likely to be. A Saturn mass rogue inferred to lie within the Milky Way disk becomes part of the disk population, moving with typical stellar motions. This helps relate the detection to theories of ejection in disk star formation environments. It also affects how likely it is that a host star could be hidden. If the lens were actually a planet bound to a star, the host star might contribute light. If no such light is detected to the limits of the data, the case for a truly free-floating planet strengthens, though it may not be absolute. The absence of host star light is a constraint, not a direct image. Such a measured example also helps sharpen the meaning of the term rogue planet in observational work. In casual language, rogue can imply mystery. In scientific terms, it describes a planet mass body whose gravitational signal appears without an obvious host. The distinction between a truly unbound planet and a very wide-orbit planet is handled through modelling and constraints, not through naming. A robust mass estimate and distance estimate allow those constraints to be stated plainly. They also allow survey predictions to be checked. If a mission predicts it can detect and measure hundreds of Earth mass rogues, it is reassuring to show that the method already works on at least some planetary mass objects. The measured Saturn mass case also adds context to how free-floating planets might be distributed in mass. If ejection is common, it may remove not only small planets, but also large ones. Large planets are harder to eject because they are massive, but they are also strong scatterers that can participate in chaotic interactions. In multi-giant systems, a giant planet can be expelled if the encounter is strong, and if the system's energy exchange favours that outcome. The probability is lower than for ejecting a smaller planet, but it is not zero. Therefore, finding a Saturn mass rogue aligns with models in which a fraction of giant planets are lost. It also aligns with the idea that ejection does not have to be limited to one mass scale. At the same time, a measured giant rogue does not resolve the question of how many Earth mass rogues exist. Giant planet events last longer, and can be easier to detect in some surveys because their lensing signals persist longer. Earth mass events are shorter and can be missed without high cadence. Therefore, a sample of measured rogues may be biased toward higher masses unless detection strategies specifically target short events. A Saturn mass detection is thus a proof of existence and measurement, not a complete census. The significance for astronomy is that it shifts the field from inference to calibration. When masses can be measured for some rogue candidates, those measurements can anchor statistical models. They can help refine the assumed velocity distributions and distance distributions of lenses. They can also reveal whether the lens population behaves as expected for disk objects or bulge objects. Each well-measured case becomes a point of contact between theory and data. For the drifting planet itself, the measured mass hints at internal structure and thermal history. A Saturn mass planet is likely to have a substantial hydrogen and helium envelope, with deeper layers under higher pressure. It retains heat for a long time because large planets cool slowly. Even without starlight, it can radiate internal heat for billions of years. Its surface is not a solid surface, but an atmosphere that grows colder with altitude. In interstellar space, the upper atmosphere would cool strongly and may develop layers where gases condense if temperatures fall low enough. Yet deep within, pressure and temperature remain high, and internal heat continues to flow outward. What remains uncertain is the planet's exact origin story. Microlensing can measure mass and distance, but usually cannot reveal composition directly. It cannot tell whether the planet formed close to its star and migrated outward before ejection, or formed farther out, or was perturbed by a cluster encounter. It also cannot easily tell whether the planet carries a moon system. These details lie beyond what microlensing usually provides. Still, the measured mass and location are enough to place the planet within a physical category and to confirm that such travelers exist. In this region, the topic moves from method to outcome, a solitary planet that can be weighed. The measured example does not stand as a singular curiosity. It stands as evidence that the galaxy's hidden population can be reached by careful geometry. It is a quiet step inward, from detection toward characterization, where a lonely world becomes not only possible but quantitatively described. Mass is a clue because mass governs how a planet forms, how it evolves, and how easily it can be removed from its birth system. When a rogue planet is inferred to have a mass comparable to Saturn, that mass points towards certain histories while leaving others less likely. It also carries consequences for what the planet can be like in interstellar space, from its interior heat to its atmospheric behavior. The story remains careful because a mass estimate does not uniquely determine a past. It narrows the range of plausible pathways and makes some pathways more natural than others. In a typical planetary system, a Saturn mass planet forms by building a solid core and then capturing gas from the protoplanetary disk. This process requires a disk that is still gas-rich and a core that reaches a critical size before the disk disperses. Such conditions are common enough to produce many gas giants in the galaxy, but they are not guaranteed in every system. A Saturn mass rogue therefore suggests it was once part of a system capable of giant planet formation. That might be a system with a relatively massive disk, or one where the timing of core growth and gas capture aligned well. This is not speculation beyond consensus. It is a general inference from the standard core accretion framework, used to explain gas giant formation in many observed systems. Once formed, a giant planet can take part in the gravitational reshaping of its system. If there are multiple giants, their mutual interactions can become unstable. In such systems, ejection of one giant is possible, though less common than ejection of a smaller planet. The reason is that in a close encounter, the planet that is easier to accelerate to escape speed is often the lighter one. Yet when two giants interact, the energy exchanges can be large, and the outcome depends on geometry and timing. A Saturn mass planet could be expelled by a more massive giant, or by a sequence of interactions involving multiple bodies. It could also be expelled if the system includes a stellar companion that perturbs orbits and triggers scattering. These are known mechanisms in dynamical studies of planetary systems. An alternative is that the planet formed on a wide orbit where it was less tightly bound and easier to remove. Wide-orbit giant planets are observed in some systems, though they are less common than close-in ones. a planet formed far out can be nudged into escape by fewer or weaker encounters. It might be more vulnerable to external perturbations from passing stars in a cluster. If the planet was on a wide orbit during the cluster's dense phase, a passing star could lift its orbital energy and help unbind it. In such a pathway, the planet's ejection may not require an intense multi-giant scattering phase. It could be driven by the environment. This remains dependent on the planet's initial orbit, which is not measured by microlensing. The mass also shapes the planet's thermal evolution. Larger planets have larger heat content and can cool more slowly. They can retain internal heat from formation and continue to release it for billions of years. In a gas giant, heat transport occurs through convection and radiation in different layers, with the details depending on composition and opacity. In interstellar space, the absence of stellar heating changes the outer atmosphere most strongly. The deep interior does not care whether starlight is present. It continues to cool according to internal physics. The planet's total luminosity becomes low, but not zero, and it declines with time. This internal heat can matter for the planet's outer layers. A gas giant atmosphere without stellar irradiation can become extremely cold at the top. In such conditions, some gases can condense and form clouds or hazes. Water, ammonia, and methane clouds are familiar in the solar system's giant planets, formed in their cold upper atmospheres under sunlight-modified temperature profiles. In interstellar space, temperature profiles would be different because there is no strong external heating at high altitudes. The atmosphere might become more uniformly cold, with a strong gradient from a warmer interior to a colder exterior driven purely by internal heat flow. The exact cloud structure would depend on chemical composition and pressure-temperature profiles that are not directly measured. What can be said is that condensation becomes more likely in the upper atmosphere as temperatures drop, and that such condensation can change how the planet emits infrared light. A giant planet's moons, if any survive ejection, add another layer. A moon orbiting close to a giant planet can experience tidal heating, which is heat produced by repeated flexing due to changing gravitational pull. Tidal heating is strongest when the moon's orbit is slightly eccentric. In the solar system, this can keep moons warm inside, even far from the sun. A rogue giant planet with a moon system could therefore carry internal heat not only in the planet but also in moons. Whether such a configuration survives ejection depends on the scattering history. It remains uncertain for any specific rogue planet, yet the physics of tidal heating is well established, and the possibility exists in principle. The mass also informs how the object is classified against other free-floating bodies. A Saturn mass object is firmly planetary in mass and does not approach the boundary where deuterium fusion becomes possible. This reduces the plausibility that it formed as a brown dwarf by direct collapse, though not completely, because formation conditions can be complex, and fragmentation models can produce low-mass objects in some circumstances. Still, in the current understanding, a Saturn mass lens strengthens the interpretation that at least some rogues are true planets that were once bound and later expelled. For population models, each measured mass acts as a test. If many rogues cluster around certain masses, that could reflect typical outcomes of scattering. For example, if systems tend to eject smaller planets more easily, then low-mass rogues might be more common, but harder to detect. If ejection of giants is rarer, then giant rogues might be fewer but easier to find due to longer microlensing events. Survey results must disentangle these effects. The measured giant rogue does not settle the balance, but it provides a ground truth point that helps calibrate the interpretation. In this region, mass becomes a bridge between observation and origin. It invites careful inference without claiming certainty. A Saturn mass rogue likely once belonged to a planetary system, because that is a common pathway for building such a mass. It may have been expelled by scattering among giant planets, or by perturbations in a cluster, or by the influence of a companion star. The precise route remains unknown. What is known is that gravity can remove planets from systems, that microlensing can weigh at least some of those travellers, and that a giant planet drifting in the dark remains a physical world with an interior, an atmosphere, and a long cooling future. A single rogue planet event is a measurement of one object. A population of events becomes a statement about how common such objects are. Microlensing surveys are built for this step inward, from individual detections to demographics. They monitor millions of background stars and count how often lensing occurs with different durations and shapes. From those counts, they infer how many lenses of different masses must exist in the galaxy to produce the observed rate. The inference is statistical, and it depends on how efficiently the survey can detect events of different timescales. Detection efficiency is central because short events are easy to miss. An event lasting only a few hours can peak and fade between measurements if the cadence is too slow, or if clouds, daylight, or scheduling gaps interrupt observations. Even if the event is recorded, noisy data can make it hard to distinguish from other variability. Therefore, surveys have a bias. They are naturally more sensitive to longer events. This bias can be corrected, but correction requires careful modelling of the survey's observing pattern, its noise properties, and its selection criteria. These corrections are not optional. Without them, the inferred population would be skewed toward heavier lenses. The mass distribution of rogue planets is not observed directly. What is observed is a distribution of event timescales. Timescales can be converted into a mass distribution only by using assumptions or constraints about typical lens distances and velocities. When parallax measurements are available for a subset of events, they help anchor those assumptions. When they are not, models of the Milky Way are used. These models include the density of stars in the disk and bulge, the distribution of their motions, and the likely distances to source stars. They are informed by many observations, but they still have uncertainties. Therefore, population estimates of rogues often come with ranges rather than single values. Another challenge is distinguishing truly unbound planets from planets bound to stars at very wide separations. A wide-orbit planet can lens a background star without an obvious simultaneous signal from its host star if the projected separation is large enough. In such a case, the event resembles that of a free-floating planet. Whether the host star's lensing signature is detectable depends on the alignment and on the star's mass and distance. If the host star is faint or distant, its light may not be visible either. Therefore, some fraction of short microlensing events could be caused by bound planets, whose hosts are not detected. Surveys attempt to estimate this fraction using models of planetary systems and detection probabilities, but the separation is not always clean for individual events. Despite these complications, population studies can still reveal meaningful patterns. If surveys find more short-duration events than expected from known stellar populations, that excess can indicate a population of planetary mass lenses. If the excess is concentrated at timescales consistent with Earth mass lenses, that suggests many low-mass rogues or wide-orbit planets. If the excess is at longer timescales, that suggests higher mass objects such as giant planets or low-mass brown dwarfs. The pattern helps test formation and ejection models. Ejection models tend to predict that lower-mass planets are more easily removed because they require smaller velocity changes to escape a star's gravity, and because massive planets can scatter them efficiently. This would imply a potentially large population of low-mass rogues. At the same time, giant planets have larger lensing signatures and produce longer events, making them easier to detect. Therefore, the detected sample might overrepresent higher masses even if lower masses are more numerous. The true population could be dominated by small objects that current surveys cannot detect well. This is why the planned sensitivity of future surveys to short events matters. It is also why claims about the absolute number of Earth mass rogues must be made with care and tied to survey limits. There is an additional layer of uncertainty that comes from the fact that microlensing surveys usually target specific fields. Many focus on the galactic bulge because the background star density is high. This means the detected lens population is weighted toward objects along those lines of sight. Those lines of sight include both disk and bulge lenses. If the rogue planet population differs between disk and bulge due to different star formation histories or different dynamical environments, the bulge-focused sample might not represent the whole galaxy uniformly. Models can attempt to account for this, but it adds complexity. Still, the broad scientific aim is clear to determine whether the galaxy contains as many rogue planets as stars, fewer or more. Different studies have suggested different answers depending on data sets and assumptions. Some analyses have indicated that Jupiter mass rogues might be common, while others have placed lower estimates. For Earth mass rogues, the uncertainty is larger because of detection challenges. The field therefore benefits from methods that can measure masses more directly, and from surveys that can detect short events reliably. In this region, the narrative stays with demographics as a careful science. A rogue planet population is inferred, not counted by direct imaging. The inference is grounded in gravity and in large data sets, and it is limited by cadence, noise, and degeneracies. As more events are collected with better sampling, the distribution becomes clearer. As more events include parallax or other constraints, the mapping from timescale to mass tightens. Each improvement reduces the reliance on broad assumptions. The movement inward from population counts is toward a new generation of surveys designed to detect and measure large numbers of low-mass rogues. The goal is not only to confirm that rogues exist, which is already supported, but to determine how their masses are distributed and how often they occur. With a well-measured census, theories of planet formation and dynamical evolution can be tested against the galaxy's inventory of worlds that no longer belong to any star. A dedicated survey can turn rare events into a steady stream of measurements. The Nancy Grace Roman Space Telescope is designed with features that make it well suited for microlensing a wide field of view, stable space-based imaging, and the ability to monitor dense star fields with frequent observations. In microlensing, these features translate into a practical advantage. Many stars can be watched at once, with consistent photometric quality, and with fewer interruptions than most ground-based campaigns. This is especially important for short events that signal low-mass lenses. In microlensing terms, sensitivity to Earth mass rogue planets requires three things. The first is cadence, meaning observations must be frequent enough to capture events lasting hours. The second is precision, meaning brightness changes must be measured reliably, even in crowded star fields where many stars overlap in the same patch of sky. The third is sheer scale, meaning the survey must monitor enough stars long enough that rare alignments occur often enough to build statistics. Roman's design targets these needs by combining a large observing area with repeated imaging of the same regions. Predictions from modelling studies suggest that Roman could detect a large number of rogue planets, including objects with masses comparable to Earth, through microlensing events. The scale of the prediction depends on assumptions about how many rogue planets exist per star and how their masses are distributed. It also depends on the survey strategy, including how long the microlensing campaign runs, which fields are chosen, and how often they are observed. Even with uncertainty, the core expectation is stable. A wide-field space telescope watching the galactic bulge should find many microlensing events, and among those events should be a measurable subset produced by planetary mass lenses without detected hosts. Roman's role is not only detection but characterization. The stable, high-quality light curves from space can reveal short events more clearly than ground-based data alone. Roman can also observe in infrared wavelengths that penetrate dust better than visible light, allowing it to see deeper into crowded and reddened regions toward the galactic center. This increases the number of usable source stars. With more source stars, the event rate rises. With better sampling, the light curves become more informative. This combination helps constrain lens properties more effectively than many earlier surveys. Even with Roman, some limitations remain. A single space observatory provides one viewpoint. Parallax measurements for individual events are improved when observations are made from two separated locations, such as Earth and Roman together. Roman's orbit and its separation from Earth can provide a baseline that allows parallax to be measured for some events, especially if ground-based networks also observe the same events. The quality of such parallax measurements depends on the baseline at the time, the event timescale, and the ability of both platforms to observe the event with good cadence. In some cases, Roman's data alone may still leave mass distance degeneracies, but for many events it can provide strong constraints, and for a subset it can enable mass estimates that are far tighter than single ground surveys could achieve. Roman's predicted yield of Earth mass rogue planets has been described in terms of hundreds under certain assumptions. The number is not a promise. It is a model-based expectation. It assumes a particular distribution of rogue planets and a particular performance of the survey. The scientific value is that even a smaller yield would be transformative, because Earth mass rogues are currently hard to detect and poorly constrained. A sample of dozens with good light curves would already allow strong tests of population models. A sample of hundreds would allow comparisons across mass bins and across different galactic environments along the line of sight. The presence or absence of an Earth mass rogue population has implications. If Earth mass rogues are common, it suggests that low-mass planets are frequently ejected, or that a significant fraction of planetary mass objects form in a way that does not bind them to stars. If Earth mass rogues are rare, it suggests either that ejection is less common for small planets, or that most small planets remain bound, or that wide-orbit-bound planets dominate the short-event population. Roman's survey is aimed at providing data strong enough to distinguish among these possibilities through the observed timescale distribution, the frequency of short events, and the statistical constraints on lens masses. Roman also fits into a broader ecosystem of observations. Ground-based surveys continue to monitor the bulge and can provide complementary coverage. If Roman detects an event, ground observatories may provide simultaneous data from a different location, enabling parallax. Ground observatories can also monitor in different bands, helping to characterize the source star and to control for blending, the effect of light from neighboring stars contaminating the measurement. Blending is a known challenge in crowded fields. Space-based resolution reduces it, but does not remove it entirely. Combining data sets can improve confidence in event interpretation. Within the inward progression, Roman represents a move from sparse examples to a systematic census. It is a tool designed to map the hidden distribution of planetary masses, including those that are cold and alone. the science remains careful detection does not always equal unbound status, and mass estimates carry uncertainties. Yet the combination of wide coverage, stable photometry, and high cadence makes Roman a natural instrument for turning rogue planet studies into a statistical field with measured distributions rather than only scattered events. In this region, the drifting world is no longer only an occasional signal. It is part of a forecasted population that a single mission could reveal in large numbers. The key shift is scale. With enough events, uncertainties that plague individual detections can be averaged down, and the distinction between different population models can emerge. Roman is a step inward toward that clarity, where lonely worlds become a measurable component of the galaxy's planetary inventory. A planet drifting without a star is still a world with layers, materials, and internal processes. What changes is the boundary condition at the surface. Starlight is absent as a dominant heat source, and the surface becomes a place where energy mostly leaves rather than arrives. From that outer boundary, the physical story moves inward through temperature, pressure, chemistry, and time. The planet's internal heat becomes the main driver of any remaining activity, and the planet's ability to hold that heat depends strongly on mass and composition. For a rocky rogue planet, the interior stores heat from formation and generates additional heat through radioactive decay of elements such as uranium, thorium, and potassium. This heat production declines slowly over billions of years as radioactive isotopes decay. In a starbound world, sunlight and greenhouse effects can dominate surface conditions, but in a rogue world, the surface temperature drops toward a value set mainly by internal heat leakage and by the weak background radiation of space. Over time, the surface can become extremely cold, with volatiles freezing out and forming stable ices if they are present. The interior, however, can remain much warmer. Heat travels outward through the mantle and crust by conduction, and if the interior is hot enough and the rock can flow, by convection, the slow movement of material driven by buoyancy. A thick insulating layer can slow cooling. Ice is a good example. If a rocky planet has water, its surface water can freeze into an ice shell when starlight is removed. That ice shell can be many kilometers thick, depending on heat flow and composition. Beneath the ice, if the internal heat flux is sufficient, liquid water can persist as a subsurface ocean. This is not a general promise, but a physically grounded possibility known from icy moons in the solar system, where subsurface oceans are inferred to exist under ice shells due to internal heating. In a rogue planet, the heating would come mainly from radioactive decay and leftover formation heat, rather than from tidal heating by a giant planet, unless the rogue planet carries a moon system that provides tides. Whether the heat is enough depends on planet size and composition. A larger rocky planet holds heat longer and has more radiogenic material in total, making subsurface water more plausible for longer spans. The pressure at the base of an ice shell increases with depth. At sufficient pressure, ice can change phase into denser forms that behave differently than the familiar surface ice. These high-pressure ice phases can separate liquid water from the rocky sea floor, potentially limiting chemical exchange between rock and ocean. Chemical exchange matters because it can provide energy sources for chemistry, including the kinds of chemical gradients that can support microbial life in Earth environments. In a rogue planet, whether rock and liquid water remain in contact depends on ocean depth, ice thickness, and internal structure. Observations do not currently provide these details for any specific rogue planet. The physics provides possible internal architectures, not confirmed ones. For a gas giant rogue planet, the situation is different. There is no solid surface in the usual sense. The visible boundary is an atmosphere that grows colder with altitude. Without stellar heating, the upper atmosphere cools strongly and can become extremely cold. In such cold, certain gases and compounds can condense, forming clouds and hazes. The interior remains under high pressure and temperature and continues to radiate internal heat. Gas giants cool slowly, and even after billions of years they can remain warmer inside than their environment. The outward heat flow sets a temperature profile in the atmosphere. Without sunlight driving weather patterns, atmospheric circulation would be shaped by internal heat, rotation, and the physics of gases. The details of such circulation are not well constrained by observation for rogue planets. What is clear is that internal heat and rotation can still sustain winds and layered structures, even if the overall energy budget is smaller. A planet's magnetic field, if present, is another inward feature with outward consequences. Magnetic fields are generated by motion of electrically conducting fluids in the interior, such as liquid iron in a rocky planet's core or metallic hydrogen in a gas giant. A magnetic field can deflect charged particles and shape how cosmic rays and stellar winds interact with the planet. In interstellar space, there is no nearby stellar wind, but there are still energetic particles. A magnetic field can reduce particle penetration in some regions and concentrate it in others. This can affect surface chemistry on an airless or thin atmosphere body, and it can shape auroral emissions in the upper atmosphere of a giant planet. Such emissions would be faint but could, in principle, exist. Over long times, the planet's surface becomes a record of exposure. Cosmic rays and ultraviolet photons in the interstellar medium can break molecules and create new ones on icy surfaces. This can produce complex organic compounds and darken the ice, a process seen in cold solar system bodies that are exposed to radiation. Micrometeoroid impacts can churn the top layer, mixing fresh ice with processed material. If the planet once had an atmosphere and later lost it by freezing out, the surface can hold layered deposits that reflect that collapse. If the planet had liquid water that froze, the ice structure can preserve traces of former flow or cracking, depending on the stresses involved. These are general physical expectations, not claims about any specific object. The most inward layer is time itself, expressed through cooling. A rogue planet's internal heat declines. Its surface becomes colder. Any subsurface ocean, if present, can eventually freeze unless heat flow remains high enough. A gas giant's emitted infrared light fades with age. In this way, a rogue planet's present state is a function of when it formed and how it formed, but also of how long it has been alone. Across all types. The unifying fact is that being starless does not make a planet inert. It changes the energy sources. It makes internal heat more important than external light. It makes chemistry slow and cold at the surface while allowing warmer conditions deeper down. It turns the planet into a traveller with a quiet interior gradient, shedding heat into space and carrying its history in layered materials. The science of these worlds is still young because detection is hard and direct measurements are scarce. Yet the physics is clear enough to outline the main structure's cold surfaces, slow radiation processing, long-lived internal warmth, and, in some cases, hidden water kept liquid beneath insulating shells.